Now, it is my distinct pleasure to introduce to you today's speaker, Pierre Mester. Pierre is a good friend. Pierre got his degree in Switzerland and then another degree in Germany. He came here to do a postdoc. Then he disappeared back into Germany to be part of the Max Planck Institute in optics. And then he came back where he's a Regents Professor, which is the highest award that we can bestow on any of our faculty. He's a Humboldt Fellow, and I can go on and on about all his awards. He's unfortunately just retired, but he hasn't retired. He's become the chief editor for the American Physical Society, which is a big deal if anybody's interested in physics. All the important thing is written there. And today he's going to tell us a little bit about the wondrous physical world when you go really, really small. Pierre?
Well, thank you, Joaquin. Has anybody looked at the weather forecast for New York today? It's great to be in Tucson. So thank you for inviting me. And before I start, there is one person that Joaquin forgot to thank for all these extraordinary lectures which we have year after year after year. And it is Joaquin Ruiz, because none of that would happen without him. So thank you very much, Joaquin. So this is the last lecture of this physics series. And I'm actually shocked that there is still anybody in the room, because when I was young and I would go to parties and suddenly some lady would come close to me or people would come close to me and they said, "What do you do?" And I would say, "I'm a physicist." They would all walk away. Okay. So we had 4 extraordinary lectures where the speakers tried to explain what we do to understand what's next in physics. And what we've seen is that a lot of this work is done in extraordinarily extreme conditions, be it near a neutron star or a black hole, or in these extraordinary accelerators which are built, the LHC accelerator in Geneva. And really to understand what we don't understand in physics, or in astronomy, we have to very often go to these extraordinarily extreme conditions. But what I'd like to do today is to take a step back and tell you that things are even extraordinary and bizarre and strange in our everyday life. And about 100 years ago, very, very bright people invented a new theory of physics, which is called quantum mechanics. And I will show you that quantum mechanics has changed our lives completely, and you could not live without quantum mechanics anymore, except you don't know that or you don't care about that. But the other thing which is really important is that in addition to changing our lives, quantum mechanics has forced us to change our deep understanding and things about what is reality, what is locality, and things like that. So let's see if it works. I'm a theorist, I break everything. So I think Keith Dean has told you something very, very important about what physicists do. And the first thing that we do is we try to understand what are the rules of the game, what are the laws of nature. And this is, again, what for instance, we heard when we talked about the LHC experiments trying to discover new particles, stuff beyond the standard model of physics. But there is a lot more to physics than that. And it's like if you play chess. If you play chess, it's one thing to learn the rules of how you move the pieces. But if you just learn the rules, I can bet you I know my grandson is going to beat the heck out of you. Okay. Because he's learned more than the rules. He's learned also strategies. He's learned how to exploit the rule, how to understand the profound implications, and how to do stuff with that. And this is the second part of physics. In parallel with the process of discovering new laws, we need to learn how to use these laws, how to understand what they mean. And this is a little bit what I want to talk about today, this second aspect of what makes physics so exciting. And basically, I will talk to you about 2 mysteries. So there's a cat here. And this cat is here for at least 3 reasons. The first one is that cats are very mysterious animals, and a lot of what we're going to talk about is mysterious. We know the Cheshire Cat, which was a very strange cat in Alice in Wonderland. Most of you probably also know about the Schrödinger cat, which is both dead and alive. And so I thought that if I keep this cat here, on some of the slides, this cat will come back. And this is a time when you want to take a deep breath because it's going to become really weird. And I want you to think a little bit this. So the cat is going to help guide us through this business. And there are basically 2 mysteries I want to talk about. The first one is something that you may have heard about a bit more. It's so-called wave-particle duality. This was something which was understood, not understood, but started about 100 years ago, 90 years ago. And basically, it tells you that quantum objects are waves, except if you look at them. Okay. So that's the first mystery we're going to talk about. And the second mystery is something that Einstein called spooky action at a distance. And it has to do with the fact that in some situations, you can have 2 particles, one on the moon and one on the Earth, or even more unrealistically, one in San Francisco and one in New York. And you cannot describe these 2 particles independently. What a particle does profoundly and instantaneously impacts the other particle. So this is the 2 mysteries. And the bottom line of my lecture is going to be that these 2 mysteries lead to 2 really key consequences. The first one is that we have to rethink what we mean by reality. And the second one is that we will need to rethink what we mean by locality. Reality is the idea that the properties of objects exist whether I look at them or not. So basically, Joaquin exists with a beard whether I look at him or not. That's reality. Locality has to do with the fact, which Einstein made very clear, that no information can propagate faster than the speed of light. And we're going to have to revisit these 2 self-evident truths, if you want, in the context of quantum mechanics. Okay. So let's try to start a little bit slowly. And it's always a good idea to start with talking about light, because for centuries, scientists have been worried quite a bit about light. What is light? How do we process images? All these kind of aspects of light are extremely fascinating. I could give a whole lecture or series of lectures on that, but I don't have time. So I will start at Newton. Newton was a cranky old man. He looks cranky. And he was cranky, and he looks cranky here. And he actually was one of the most important scholars of optics until the 18th and 19th century. He wrote a wonderful book called Optics, where he studied the reflection of light, the refraction of light. He studied how light, if you put light through a prism, gets broken into colors. And he came to the conclusion that light was made out of streams of little particles. Okay, that was his view of the world. Okay. So light was particles for Newton. And this view of light stayed with us for well over 100 years until another great character came around. His name is Thomas Young. He was actually a polymath. He was a medical doctor. He was very interested in the eye. He's the first who understood how the eye changes its shape so that we can focus objects at different distances. He also was the first to understand what astigmatism is. But in addition, he was also an Egyptologist. He made key development which led then to the translation of the Rosetta Stone by Champlain in France. And so he did all kinds of things. He sort of did mechanics. There is a wonderful book. If you don't have anything to do, you should read this book. The title of the book, Thomas Young, The Last Man Who Knew Everything. An absolutely remarkable book. And he studied light as well, because he was interested in the eyes, so therefore he thought, I need to study what light is. And he made a very simple experiment, which I show here. where he took a little screen and he cut 2 slits into this screen, and he shone a beam of light through that screen. Okay, very, very simple experiment. And we all know what to expect in this experiment, right? What do we expect? Well, light is made out of little particles, so the particles will go either through one of the slits or the other. So we are clearly going to get 2 bright lines on some detector on some screen behind this double slit. This is completely obvious, right? So why bother do the experiment? But anyway, he did the experiment anyway. He probably didn't have anything else to do. And what he found is completely different. He found this pattern of rays, which are called interferences. And interferences were well known and are very well known. For instance, if you are on a very quiet pond and you put 2 little pebbles, throw 2 little pebbles in this pond, you get 2 waves, which are going to come close to each other. And when they interact, you get these waves, you get this interference pattern, okay? So, like on that. So he concluded that actually light is not made out of particles, but it made waves, okay? So just to make sure that we keep that in mind, because it will be somewhat important, if light is made out of particles, we would get a pattern like that, 2 bright spots. If it's made out of waves, we will get something like that, the interferences that Young observed. So he wrote a paper, and then he realized that it's not a good idea to contradict Newton. So here's the paper. I don't want you to read it, but I just want to show you a review of his paper. And now I'm an editor of a bunch of journals, so I see reviews like that. Maybe not as eloquent, but to show you that physicists, contrary to popular belief, are not always nice guys. So here's what this review said. The paper contains nothing that deserves the name either of experiment of discovery, and it is in fact destitute of every species of merit. And then it got personal. More fancies, more unfounded hypotheses, more gratuitous fictions, all upon the same field on which Newton trod, all from the fertile yet fruitless brain of the same eternal Dr. Young. This is not nice. So, yeah. So it's tough, right? You have this dogma around and you try to change it, and it's really tough. And it took a long, long time before finally people said, you know, maybe Young has something. And during the whole 19th century, people worked very hard at that. And the culmination of this work was the work of Maxwell, James Clerk Maxwell, who explained light in terms of electromagnetic waves. I think that Keith Dean has talked about that. These are electromagnetic waves which propagate, surprise, at the speed of light, okay? So this was perfect. And this is one of the culminations of 19th century physics. It's also boot camp for theorists. Okay? This is very hard physics, and it explains a great deal of things, and it's wonderful. It's wonderful, except there was just one small problem with Maxwell's equations and this theory of light, and this is something called blackbody radiation. So let me tell you what blackbody radiation is. Blackbody radiation has to do with the light emitted by something called a blackbody. So what is a blackbody? This is what I've tried to show here. It's basically a little cavity, a hollow cavity, which is black for everything. So it absorbs all colors of light perfectly. Now, of course, if the system wants to reach a temperature and not melt, it has also to emit this light. So there is an equilibrium between the light which is absorbed and the light which is emitted. The blackbody is that this works for every color in the spectrum of light. And then you can make a little pinhole and see how much intensity you have for different colors of this light. Okay? It's called the spectrum of blackbody radiation. And you can measure that, and you find this result here. So on the horizontal axis, I have the wavelengths of light. It's just the color of light, okay? And on the vertical axis, it's the intensity. And I have 3 curves of different color, a red curve, a yellow curve, and a blue curve for 3 different temperatures. So at 3000 Kelvin, you see the peak, the most intensity is around 1 micrometer, which is infrared light. As you heat up your cavity, you make it 4000 Kelvin, the peak of the intensity shifts to more visible light near the red. And if it gets even warmer, it shifts toward the blue. These are things that people can measure extraordinarily accurately. This is the blackbody spectrum. And the white curve is the classical theory for 5000 Kelvin, the theory of Maxwell. And you don't have to have a Nobel Prize to see that the blue curve and the white curve don't quite match. Now, physicists are highly trained people. We go through undergraduate school, we do 4 years of undergraduate school, we do a bunch of years of graduate school, we become postdocs, we go through tenure track and all that. So we have really very fancy technical words to explain this kind of problems. Okay, that's the problem. And this is the technical word. So it means we have a problem. Everything was perfect except for just this one experiment. Nobody could throw away the blackbody, and the experiments were very good, and we had a problem. So it bothered people a great deal. And one of the folks who spent a lot of years trying to figure out what was going on was a physicist in Germany named Max Planck. And finally, out of desperation, he came out with a crazy new assumption based on nothing. He said, light is made of waves, but these waves come in little bundles of energy which can have only discrete values, which are called quanta of energy. He invented the word quanta of energy. Now this is what we would call photons. It was completely out of nowhere. It was just desperation. He came up with this, and then Einstein worked with this hypothesis. He was able to explain a bunch of other things. So suddenly we were back in a situation, this kind of perfect compromise where light is both waves and particles. Okay. So this was quite a big leap of faith in a sense, but it explained this blackbody theory, system and all kinds of other things. And then there was a prince. You know, every story has to have a prince. So we have a French prince, and this is Prince Louis de Broglie. And he went one step further. He said, well, if light is made out of objects which are both waves and particles, maybe everything is made out of wave of particles. Every particle is made out of wave, has a wave aspect and a particle aspect. For instance, electrons. And this was, again, a huge, it was his PhD thesis. He was in his 20s, okay? And if you did that, you could develop some wonderful theory, but it was, again, not clear that it was right until in 1927, so just 90 years ago, there were experiments done in the United States by Davison and Germer, which actually proved that electrons behave like waves. So all this story, which took about 20, 25 years, led to the development of quantum mechanics. These are two of the big heroes, Erwin Schrödinger and Werner Heisenberg. Now, you have to understand that Heisenberg was like 25 years old when he did that, and Schrödinger was the old guy. He was almost 40. Don't you hate them? They have no respect. But I guess you had to be really young to be so crazy and creative and invent this new theory. And it worked. And quantum mechanics has been developed to an exquisite level of understanding, and it's changed your life. How has it changed your life? If you understand quantum mechanics, if you understand that electrons are waves, you can understand why some solids are metals, some are insulators, some are semiconductors, and all kinds of things like that. And this led to extraordinary developments. You would not have integrated circuits if you did not understand quantum mechanics, if somebody did not understand quantum mechanics. You would also not have cell phones. You would not have a GPS system. What else would you not have? You would not have the internet, that's for sure. You would not have lasers. You would not have laser surgery. If you did not understand how atoms interact with magnetic fields or with light, you would not have magnetic resonance imaging. Did I get it right? I did. And you would not have solar panels. So it's really changing our life, okay? Everything we have in this room, I don't know how many people have a cell phone in this room, but I would bet it's more than one. And this is all based on understanding quantum mechanics, understanding this wave-particle duality. Of course, there are also some bad things. And as somebody pointed out, a single nuclear weapon can ruin your whole day. So, but anyway, so this is really what quantum mechanics has done for us, thanks to people really understanding how to play this game. But I want to go back a little bit, because now we know how to do that, but do we understand the real deep implications of quantum mechanics? And this is what I want to spend a few minutes going back to. So I want to go back to this double-slit experiment. Okay? Because I told you that electrons are particles and waves, or photons are particles and waves, but I've not told you how strange that is. And now I want to tell you how strange that is. So I'm going to redo the Thomas Young experiment, but instead of sending a beam of light or a beam of electrons through my double slit, I'm going to send one electron a day, or maybe one electron every week, or one electron every minute. It doesn't matter, but very rare events, okay? One electron, and then you wait. And now we can do that because we have all these graduate students who have nothing better to do. So they can certainly do this kind of experiments. So let's see what happens. So what do you expect will happen? Well, what I expect will happen is, no, it's just one electron, right? So the electron is going to go through one of the holes and land on the screen, and I will get a little dot on my detector. And I do. So this is after a week, okay? You have 7 or 8 dots. There is no big deal here. But now I can do it for a month, and I get more dots. And then I do it for a year, and suddenly, wow, I get these interferences. This is completely crazy. You have to understand this is completely crazy, because I did it one electron at a time. How do they know? How do they know? But I'm a physicist, so I say, well, I'm going to trick these darn electrons. I'm going to check through which hole they went. And I can put a little detector. Okay, so here I have my experiment. I put a magnifying glass. Actually, it's going to be a slightly fancier detector. And I'm going to just look through which hole this darn electron went. We can do that. Do the experiment. You measure through which hole your electron went. Boom. The interferences disappear. Okay. There's the cat. What have we learned? Is my electron a wave or a particle? If you look, if you observe which way the light went through, or the electron, it appears to be a particle. If you don't look, it behaves like a wave. What it means is that you can change reality by deciding what you're going to look at. Okay. And this is the new thing that quantum mechanics does for you. It forces you to change your understanding of reality. Okay. John Wheeler. You may have heard about John Wheeler in other lectures, because John Wheeler was a great expert at general relativity. He coined the word black hole, I think, but he was also a great expert at quantum mechanics. And he was also a magician with words. And he coined this sentence to describe the situation. What we call reality arises in the last analysis from the posing of yes or no questions and the registering of equipment-evoked responses. All things physical are information theoretic in origin. Here's another way to say it. He said, no phenomenon is a phenomenon until it is a recorded phenomenon brought to a close by an irreversible act of amplification. It's a very, very profound statement. Feynman, everybody has heard about Feynman, put it another way, which is actually very important to also digest. It is impossible to explain this in any classical way. It has in it the heart of quantum mechanics. In reality, it contains the only mystery. We cannot make the mystery go away by explaining it. We can just tell you how it works, but not why it works. Okay. So this wave-particle duality, which we use to make transistors and ICs and all that, has actually much more profound implications in a sense, because it forces us to revisit what we mean by reality. And the reality is that I'm going to be in real trouble with time. Okay, so this was my first mystery, where I said I would talk about two mysteries. Now I'm going to get to the second mystery, which Einstein was such a brilliant man, he always brought up new, extraordinary concepts. And this is spooky action at a distance. So now we're going to talk about spooky action at a distance. And this is a bit tricky, so I actually will need some help. So I need two assistants. Now, I'm not going to ask any of you to come up there. I don't want to impose that on you. So I have two virtual assistants. And in physics, we used to call them A and B, but then we decided to be nice and we had to be friendly. So now we call them Alice and Bob. So I want to introduce you to Alice and Bob. So who should Alice be? I think it's pretty obvious. Alice should be Alice from Alice in Wonderland. So here is Alice. And Bob, for Bob, we need somebody who is a very distinguished person, probably somebody with a Nobel Prize, right? Nobel Prize gives you the kind of, gravitas that you need. So here is a Bob with a Nobel Prize. So this is Alice and Bob, okay? And they will be with us for a little while now. So let's first do a very simple experiment. We're going to play with coins. So we have a bag of coins, and both Alice and Bob take one coin each out of this bag. And then Alice flies to New York, Bob flies to Los Angeles, and they start playing head and tail. They start flipping their coin. Okay? So let's do it once, and Alice finds tail, Bob head. Do it again. Alice head, Bob tail. Do it again. Head, tail, tail, head, tail. That's what they find. This should bother you. Does it bother you? Good. Why does it bother you? Because you never find a case where they get the same thing. Right? These are independent coins. He took his coin, she took her coin. She went to New York, he went to Los Angeles. There would be many situations where they both flip to head or to tail. We don't have any of those here. So this is impossible, right? This is impossible. Oops, there was another one. It's impossible, but what I'm going to show you, or try to convince you, is that in quantum mechanics, this is actually possible. Now, Alice comes and says, there is no use trying. One can't believe impossible things. But fortunately, the Queen of Hearts comes and answers, I dare say you haven't had much practice. When I was your age, I always did it for half an hour a day. Sometimes I believe as many as 6 impossible things a day. All I want you to do is to believe one impossible thing today. Okay? or maybe 2. OK, so let's try to do some impossible stuff. And to do that, I will tell you something that we can do in physics. We can do something which is called, we can create something called two-state particles. Let me tell you a little bit how this works. It's actually very simple in principle. In practice, only experimentalists can do that. But basically, the idea is very simple. You take a source of atoms, maybe cesium atoms or silver atoms, and you put them in an oven. And you heat them up until they start evaporating. And some of the atoms are going to exit from the oven, and then you put 2 little holes to column in to make a very nice beam of atoms. Okay? You can do that. And then you pass this beam of atoms through a magnet, which is a north pole and a south pole, and then you see where these atoms land on a screen after the magnet. And what you will find is that they will only land in 2 positions, either up or down. Okay? This is called the Stern-Galar experiment. For a given atom, you don't know it will end up or down, but they will only end up or down. So this is basically like coins. For coins, we had head and tail. For these atoms, we have up or down. Okay? So in a sense, you can think of them as quantum coins. Okay? And one thing that I also need to tell you, because it's going to be important, is that you can rotate the magnets, and what will happen is it will just rotate the thing. You still have just 2 dots. They will just be rotated like the magnet. Okay? And we are going to use that later to really confuse things even more. Okay? So these are, if you want, our quantum coins. And these quantum coins are very strange. So classical coins can have only head or tail. Quantum coins can have up and down at the same time. We talked a bit about the Schrödinger cat, which can be alive and dead. Well, it's hard to make a cat which is alive and dead, but these quantum coins, we can really make them up and down at the same time. So this is a key difference. Classical coins have to be head or tail. This can be head and tail at the same point. So now let's play with these coins. Okay, let's do the Alice and Bob experiment. So I'm going to have a source of these coins, and I can send 2 of them. But these are very special sources. You have to work a little bit at making these sources. But you can make these 2 quantum coins, these 2 atoms, you can prepare this system in such a way that if the first one is up, then the second one is down for sure. And if the first one is down, then the second one is up for sure. You can do that in atomic physics. It's not very hard. These are called entangled particles. Okay? If one is up, the other one is down, for sure. That's the thing that was impossible with the coins of Alice and Bob. But with atoms, you can do that. And so if you want to describe this system, you will say that this system is such that if one is up, the other one is down. But remember, they can be up and down at the same time. So we have the system which is up, down, and down, up. So that's the state of the system, to use the jargon of quantum physics. These are entangled particles. And now let's make some measurements. So I'm going to make an experiment where I'm going to put one of these magnets. Remember, like we had a couple of slides ago, I'm going to put a magnet to try to figure out if my particle 1 is up or down. And let's say I measure my particle to be up. So what does it mean? It means the second particle is down for sure, right? This is how these particles were prepared. So once I look and I discover that the first particle is up, look under the poof. This disappears. After I have measured the state of my first particle, the system is now in this state. The second particle is instantly in down. And this will be instantly in down even if the first particle is in New York, the second is in Los Angeles. This is what Einstein calls spooky action at a distance. Okay. Why did he call it spooky action at a distance? Because it was this instantaneous change in the system, and Einstein, who was no dummy, knew that things like that should not happen because no information can be transferred faster than the speed of light. So what's going on here? What's going on is that spooky action at the distance conflicts with the fundamental concept of locality in classical physics. And that's a problem. Okay? That's a real problem. Now, I have to make a point very clear. It doesn't mean that information can be transferred faster than the speed of light, but just the state can be changed faster than the speed of light, which is a different statement. Okay, and that's not all. He comes back. Einstein never stops annoying you. Okay. Einstein wrote a very, very wonderful paper in 1935 with his colleagues Podolsky and Rosen. This paper made everybody think, and it's almost certainly the most interesting wrong paper in the history of physics, because it really made everybody think. And he had the definition of reality, which I already hinted at earlier, which he wrote, that's his definition of reality. If without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then this physical quantity corresponds to an element of physical reality. So that's what I said about the Dean. If without, I don't have to go touch his beard, I know that he has a beard, there is an element of physical reality associated with his beard. Okay, it might be a poor element of reality, but it's an element of reality. So basically, since now you know for sure what the state of this particle 2 is without having to measure it, you know, this is the particle that you didn't look at, there is an element of physical reality associated with the state of this particle. No question. But now you can become nasty, and you say, I'm going to do another experiment. Instead of having my magnets pointing vertically, I'm going to rotate them this way. Same experiment, but now I've changed the direction of the magnet. And obviously, I can do the same argument, and I will also have an element of physical reality associated with the state of this particle along this direction. Okay? Makes a lot of sense. It should, because it comes from Einstein. Einstein makes a lot of sense. But then there is this fellow I mentioned earlier, Heisenberg, and he said, you can't do that. Not in quantum mechanics. This is no-no. It's a big no-no. It's called the Heisenberg uncertainty principle. It is fundamental to quantum mechanics. And he says that you cannot measure, I use jargon, the spin is basically this component of this particle up and down. You cannot measure this thing in a vertical and a horizontal direction at the same time. It is not allowed in quantum mechanics to do that with arbitrary accuracy. This is a Heisenberg uncertainty relation. Nobody disputes that. It's been tested and tested and tested. So here is Einstein. He says there must be an element of physical reality associated with the vertical component, an element of physical reality associated with the horizontal component. And Heisenberg says you can't measure both at the same time. So what is the conclusion? The conclusion is that quantum mechanics does not provide a complete description of physical reality. And this is the famous Einstein-Podolsky-Rosen paradox. So where does it leave us? It leaves us with a problem, which I already showed you at the beginning of this presentation, that quantum mechanics, quantum entanglement is in conflict with two fundamental tenets of classical physics, reality and locality. Okay, and we went through that. Okay, so that's pretty heavy. It's actually too heavy for me. So when you see something like that, so I have a friend who would say, that's why we drink. Okay. But another person say, I give up. Okay, I'm going to do something else. I'm going to go and start a sock factory. So now we are going to talk about socks. That should be a bit easier than to talk about these darn particles. So I'm going to work in a sock factory, and they want me to test the socks, how good they are, how well they resist being washed at room temperature, cold wash, and intermediate temperatures, and maybe hot temperatures. By the way, this is a presentation I stole from this reference, okay? So don't blame me. So here's the test we want to do. Am I losing? Okay. Will these socks survive 1,000 washes at 0 degrees, 45 degrees, and 90 degrees? But I'm a bit lazy. I don't want to do all these tests. So I'm going to take some of the socks and do them at 0 and 45. Some I will do at 0 and 90, and some I will do at 45 at 90. And I figure my boss will never see any difference. So that's what I'm going to do. So I can do this test. And what I find is something which may sound bizarre, but you will see is actually completely trivial. What we will find is the number of socks that can be washed at 0 degree and not at 45 degree temperature, plus the number that could be washed at 45 degrees and not at 90 degrees, must be larger than the number that can be washed at 0 but not at 90. Sounds strange, but let me show you why it's not strange. I have a very beautiful little picture here, which is actually due to Ken and Danny, so thank you so much for figuring that out. So here are my socks. So green is they passed the test, red they failed the test. So let's the first one, the ones which can pass at 0 degree and not at 45 degrees. So we've not made the test at 90 degree, but at 90 degree either they would have passed or they would not have passed. So my pair of socks on the left are the same as the pair on the right, except at 90 they might have passed or not have passed, okay? And I can do the same for the next test. The ones that can pass at 45 and 90, these are these guys here, but the test at 0 could be successful or not. So this is really what it means. And the one at 0 degree is 90 degrees, same thing again. The one in the middle at 45 degrees could have passed or not have passed. And now you look at this bunch of socks, and you give them letters, because we are doing science, so we put letters. And you see that these guys here, the guys B down here, it's green, red, red. It's the same as the green, red, red up here. And the green, green, red are the same as the green, green, red up in the middle. So you see these two guys are included in the other two, but the other two have more stuff. And therefore, what is in the first two is at least as much as what is in the third, okay? So it's actually kind of makes sense. And now you can make a great assumption, or you can ask a question, are particles like socks? So you can make the same estimation with particles. You change socks to little balls, okay? And you get exactly the same thing. And this is a very fundamental theorem, which is called Bell's theorem. Okay? He did it with a little bit more math, but basically that's what he did. And here is John Bell. John Bell was an extraordinarily talented theoretical physicist, worked at CERN. He was a high-energy physicist, but he also played with these foundations of quantum mechanics. And the beauty of this example with socks and particles is that this is something that you can test experimentally. The EPR paradox, for a long time, folks thought that it was more or less philosophy, but now you can test these things experimentally. And if the particles don't behave like socks, it means something fundamental. It means that quantum physics cannot be represented by a classical picture of physics. Or if you want to put it in more fancy words, if this test is failed, it rules out of description of quantum mechanics by a local realistic theory. And again, the beauty of Bell's theorem is that suddenly you can actually do the experiment. So the experiment was done, started in the late 70s and early 80s. And the way you do the experiment is pretty much what I did before, except that now having testing on just one side, you put one side at 90 degrees and one at 45 degrees to do the two temperatures, if you want the two angles now for the spins. And you can so do this experiment. and you can count. And these experiments have been done better and better and better, and they're becoming more and more sophisticated and with less and less systematic error. And the result is if the particles behave like socks, you will have this inequality. And in quantum mechanics, you can actually calculate or measure these probabilities, and you find that the first one is 0.07, the second one is 0.07, and the third is 0.25. And 0.25 is larger than 0.14, so this is violated. Okay. So particles don't behave like socks. Okay. And basically, it shows that quantum mechanics is not a local realistic theory. Okay. So Feynman is back, and he made another statement about the result of this experiment, which is the statement that you should make, that we should all make. This is why we drink. Quantum mechanics describes nature as absurd from the point of view of common sense, and yet it fully agrees with experiment. So I hope you can accept nature as she is, absurd. And unfortunately, that's true. Okay, it's completely contrary to our common intuition. We're just not hardwired to understand what nature is at the quantum level. Okay. Now, there's another quote I want to make. This is from somebody named Alain Aspect. Alain Aspect is a remarkable figure in this whole story because he started to do experiments as a graduate student. I know him quite well. And he told me that when he started to learn about that, he went to visit John Bell. Alain is in Paris, John Bell was in Geneva. And he told him, I want to do experiments. And John Bell asked him, do you have a permanent job? And Alain Aspect was a student, said, no, I don't. He said, don't do it. Okay? Because it was the best way not to get a job. But Alain Aspect, being who he is, decided to go ahead anyway. And he's become the world expert on this business. I'm sure he will get a Nobel Prize. The other reason I want to show this picture of Alain is that he makes the best duck confit in the world. And he has a cellar with over 1,000 bottles. And I want to be invited back in his house. And what Alain said is, by closing, so it was in 2015, he said that when these perfect experiments on the violation of Bell inequalities came out, and Alain said, by closing these two loopholes, which were still bothering people at once, 3 experimental tests of Bell inequalities removed the last doubt that we should renounce local realism. And the other key point that he made that other people knew, and this brings us to this second quantum revolution, is that these experiments opened the door to new quantum information technologies. And I want us to spend about 3 or 4 minutes. Where is Bo? Bo is checking time. Bo, I think it's time for a break. So I want to show you one simple example of how this new, more profound understanding of the way to manipulate the laws of quantum mechanics will lead us to new technologies. The example I want to mention is quantum cryptography. Now, we all know about cryptography. This is these techniques which make us able to communicate with our iPhones without everybody eavesdropping on us. So the idea is, let's say, here is Alice again. She wants to communicate with Bob. She wants to send him this beautiful message, very romantic message. And she doesn't want anybody else to hear this message. So the way cryptography works is that you invent a key which allows you to encrypt your system. And the key that she uses, let's say in this case, is this thing in yellow here. And the trick is that Bob also needs to know this key. So, OK, he has the key. And then once he has the key, she can just call him with the message. No, first she has to encrypt this message. And the way she does it here is very simple. If the 2 numbers are the same, it becomes a 0 in the encryption. If the 2 numbers are different, it becomes a 1. And then she sends the encrypted message, and he uses the same rule to recover his message, okay? That's how it works. And the trick of cryptography is to make these keys very safe, hard to break, and hard to steal. But it's always a problem. And people are spending actually a lot of money making safe encryption and trying to break safe encryption. So quantum entanglement allows actually to beat this. And the way it works is very simple. Instead of having a key that you share by telephone or by meeting under a tree or something, you do an experiment with these entangled particles. So let's say Alice is going to create sources of entangled particles, and she gets one of them, and Bob gets the other one. And now they're both going to measure the state of their particle, if it's up or down. And if the analyzers, if the magnets are aligned the same way, they know for sure that if they, Alice knows for sure if she measures up, Bob will have down. But if they are not aligned the same way, then there is nothing they can say. They don't know what the answer of the other will be. So all they need to do is to do this experiment, this measurement many, many times, and then they get on the phone and they share the alignments of their magnets. And maybe they will say, in the first experiment, both our magnets were aligned the same way, so I know what I measured, therefore I know what he has. And in the second one, they were not aligned the same way, we discard them. And they keep doing, and you keep only the results when you're aligned, where your magnets were aligned, so you get your nice entanglement, and you build the key this way. You never have to tell the result of your experiment, you just have to say the setting of your magnets. So can you break this way of transferring information? It turns out, that's what I said, so it turns out that you can't, in principle. And the reason you can't is twofold. The first one is the Heisenberg uncertainty principle, which we talked about. If somebody tries to make a measurement on your system, it will perturb your system in quantum mechanics, so we'll know for sure that somebody was eavesdropping. So the eavesdropper will say, well, I'm just going to duplicate your system. I'm going to make a clone of your system, make my measurements on your system, and then I will know what you have done, and I will steal your key. And you can't do that either. I don't have time to go through that. You can't do that because there is a theorem, which is called the no-cloning theorem, which says that you can only duplicate a system by losing all information. Okay. So the result is that quantum key distribution, that's the buzzword used for that, is completely safe. And this is one of the first applications in this second quantum revolution. There are several companies which sell these systems to banks mostly. There is one in Geneva, there is one in Vienna, there is one in New York. And so I was talking about that with Dean Ruiz. And he said, that's really cool because now we could have these secret informations all around the world. And I had to tell him, not so fast. Not so fast because it's actually hard. Okay? And it's so hard that the world record right now of how far you can actually transmit quantum information this way is 90 miles. And there is a dream to actually have this global quantum communication, but it doesn't work so far. And why doesn't it work? It turns out that if you want to make these experiments at very small scales in your lab, on the tabletop in your lab, it's not too hard to do. But the bigger you want to do the experiment, the harder it becomes. And it may just be impossible to do a global communication system. We just don't know. So this begs actually a couple of questions which bring the cat back. So we know how to do these quantum systems when they are somewhat small. 140 kilometers is not completely small, but it's not very big either. So this begs the question is, why don't we live in a quantum world? Why does it look like reality is the way we have this intuition for that? If quantum theory is a more fundamental theory than classical theory, why does everyday world appear classical? Another related question is, are we fooling ourselves? Quantum mechanics was actually developed to describe atoms and photons at the microscopic level. We've pushed it very hard. But is it really the fundamental theory? To which extent are these laws applicable in macroscopic systems? And a related question is, are there fundamental limitations to quantum entanglement? Not practical, but fundamental limitations. Or can we, in principle, prepare a cat in a state where it is both alive and dead at the same time? So these are very profound questions. And these are questions which bother many physicists. And there are two approaches to this question. There is what is called the shut up and calculate kind of physicist. This sounds pejorative, but it's not really. It's the way that most physicists do physics. We do our calculations. We take our system that we want to behave quantum mechanically, but we know that it's not isolated. It's surrounded by the rest of the world, and it's always coupled somehow to the rest of the world. And it turns out that the bigger your system, the harder it is to isolate it from the rest of the world. And this coupling to the rest of the world tends to make the systems behave more classically. Okay. So this is kind of the practical, the shut up and calculate, where you don't really try to understand fundamentally what the question might be. And then there are the other physicists who actually try to understand this question in a fundamental way. And they're working very hard, and they're also developing experiments jointly with theory to try to figure out if there is something fundamental here. There are some ideas from Penrose and others about the role of gravity in making systems classical. But we don't know. So I'm going to finish my talk essentially, like most of the talks have been finished, by a big question mark. And this is pretty much always the same in physics. You always answer some questions and open more problems, more questions. But I'm not completely finished, because I was told that I should also try to summarize a little bit what we have all learned. So it's 2 minutes, more or less. Okay. He's trying to kick me out. So what have we learned? And again, Einstein comes to the rescue. Einstein said so many very profound things. And one of the things he said is that no amount of experimentation can ever prove me right. But a single experiment can prove me wrong. And we had one example of that with this blackbody radiation. Okay, people did all these experiments. Maxwell was great. The wave nature of the photon of light was perfect. But there was this one experiment that didn't fit. And it changed everything. It forced people to invent quantum mechanics, this new view of reality, and all that. So this is absolutely true and profound. One experiment can force you to revisit everything. And this is exactly those experiments that we like, and this is why people go to LHC to push the limits. This is why people do gravitational wave detection. This is the motivation to push the theories, to push until we have a place where it fails, because that's when it fails that we can hopefully learn something fundamentally new. Now, I should say that this is not always an easy job. It can be quite humbling, because we have a preconceived view of things, and we have to change it. And my son, who is a very wise man, once told me that there are only 2 things that academics don't like. The first one is the current situation, and the second one is change. Okay? So there we go. Okay. So we have this problem here, but on the other hand, the payoff can be quite extraordinary, and we have seen some of this payoff today and in the other lectures as well. So this unknown and being in a situation of ignorance is actually what physicists strive for. I was preparing this slide, and I was talking to my wife, and she told me, do you really want to use the word ignorance? Because ignorance has a bad connotation. But it's not. It should not be. Okay? Ignorance is just an excuse to understand what we don't understand. Okay? So ignorance in this sense, in this very narrow sense, is actually what we strive to figure out and to clear up. This is really what keeps us going. And this is why I think there is no better job. So thank you very much.